Hey, and welcome back to Science. We've got a real treat for you today. Mr. Klein has come in to do a demonstration for us. He has the two discs in front of him that you played with at the start of the year. First of all, Mr. Klein, if you could put your hand, the back of your hand on each of those briefly. Can you tell me which of those feels warmer?
A felt warmer.
A lot or a little?
I'd say a little, a few degrees.
Okay. Go ahead and take our thermometer right there. And why don't we flip over each block just so that we don't have any thermal energy transfer from the hand. Buttons on the side. Go ahead and get even closer. Okay, what do we got for temperature on that one?
20.1 degrees Celsius.
Awesome. And then on the other one? Perfect.
20.3 degrees Celsius.
So basically, these are at the exact same temperature. Do you have any guess as to why they feel differently?
I guess my guess would be this has a smoother texture.
Okay.
So I feel like there might be more surface area that's touching my skin.
Oh, good. Okay, that's awesome. So Mr. Klein is being kind of awesome here. He's applying something that we've been using. Turns out that B is a chunk of aluminum and A is balsa wood. So it comes down to that.
Oh.
So something is jarring with him right now.
Uh-huh. Okay.
Turns out they are at the same temperature. If they were not at the same temperature, if one was colder than the room, well, what would happen? We know thermal energy transfers from higher temperatures to lower temperatures. These things have been sitting in this room for 10 years. I think they've gotten to room temperature by now. But the metal conducts thermal energy better, so it feels colder. Because if you remember, we defined cold as being the feeling when thermal energy is being taken away from you. The wood does not conduct it away from you as quickly, so even though it's the same temperature, since it's not taking thermal energy, it doesn't feel cold, it must be warm. The next aspect, he's going to put some ice cubes on here. Before you do this, what is your prediction? Which one will melt faster?
Well, based on your explanation just now, I would say that the metal one is going to pull thermal energy faster from the ice than the wood.
Okay, because thermal energy travels from the ice cube to the block?
No, energy is in the form of heat, so it would be the No, it's not in the form of heat. I'm sorry. I got that wrong.
You went to Hancock.
Okay, so I think that the energy flow is going to be from the block to the ice.
Okay, and you think the aluminum will do this better than the wood?
That's what I think, yeah.
Okay, so stop the video now and make your own prediction. Discuss it with somebody near. Awesome, we're back. If you can set one cube on each of these, I'm going to try and zoom in a little bit on this. Can you describe what you see happening for us, Mr. Klein?
The ice cube on plate B is melting, where A is not.
That pretty well sums it. That's as clear as can be. And congratulations, you nailed that one. That's awesome. Most people end up saying, ooh, this one feels warmer, it'll melt an ice cube faster. He's awesome. He caught on that this is going to transfer thermal energy better. In this case, instead of transferring thermal energy away from his hand, it's transferring the thermal energy to the ice cube. That transfer of thermal energy is called heat. But it's only when it transfers that we call it heat.
Right.
This one is simply not transferring anything. In fact, There's not even a drop of water on there. There probably is now from my hand. This is craziness. Okay, it's been a few minutes. You see that this ice cube is almost completely melted. The other one still does not appear to have done anything. That is our science fun for the day. Thank you for joining us, Mr. Klein. Okay, there's something I forgot to do here. Mr. Klein has already taken off. You'll notice what we have right here. That ice cube's completely melted, completely gone. This one still has barely even melted. It's a really cool thing I want to do here. If I hit the surface of this foam plate, of this wood plate, right there it's coming in at 19.3. If I move the ice cube right there, it's reading negative 0.1. So it's basically reading 0 degrees, 0.8. So right where the ice cube is, it's at 0. Over here, just a little ways away, it's at 19.6. And if I flip this one over on the back side, that's interesting, 17.1, where it was in contact with the tape. This one, on the other hand, I hope this still works. So it's reading 9.7. Okay, I've got a different set of these plates. If I shoot them right now before anything is on them, we have 20.7 degrees. We have 20.1 degrees. That seems reasonable. I'm going to put the two new ice cubes on here. Leave these set for a few minutes, then we'll come on back. Okay, this has literally been less than a minute. I probably should have just left it on and sped up the footage. This one, no surprise, nothing happening. 20.4 right over there. Right where the ice cube was, looks to be around 6 or 10. So it wasn't sitting on there very long. So that part of the disc is cooling down. The other part, not so much, 20 degrees. This one, on the other hand, even where there is no water, we're down at 11. Where there is water, it's also down really cold, around 9. Around 9 degrees. Most importantly, when I flip this one over, this one's at 9 degrees. The back side of this one, 19.5 degrees. Does not transfer thermal energy, so it doesn't lose it, doesn't give it away, doesn't take it in. Conductor will transfer out to things that are at a lower temperature, will transfer in from things that are at a higher temperature. Conductors, insulators, the topic for the day. See you later.